Chapter 6, Section 1 is using similar polygons. So we are not going to be talking about congruent polygons anymore. I mean, we will in the future, but for this lesson, we are talking about similar polygons and what that means. So when we talk about similar polygons, what we are talking about is that we have two shapes, two polygons, where the corresponding angles are congruent. So all of the angles, 100% of them, every single one has to be exactly the same. So one thing to notice here is this little dash, as we just called it a moment ago. This little squiggly line is not the congruency sign. It's not. It's the similarity sign. It means that two things are similar. And what does similar mean? Well, it means that two things... Okay, so two shapes that have the exact same angles. So if you think about it, what gives something the look of it is the angles, right? Like, I mean, the reason that two things look the same is because their angles are exactly the same. Like if two cars look exactly the same, it's because they have the same angles everywhere. Now, they may not be the same size. For example, a Matchbox or a Hot Wheels car can be the exact same as a big car, just a smaller version of it. So when we're talking about two things that are similar, we are talking about two things that are the same shape. They have to be the same shape, but they're not necessarily the same size. They could be the same size, but they don't have to be. For example, if you go to the Statue of Liberty, right, usually at the base of like these big monuments or things that people go to see, they're at the base, they have people who sell little models of them. The reason you buy that model is because it looks just like the real thing. Now, it's not the real size, but it should be pretty much an exact replica of the real one, just a much more condensed version. You don't probably have room to keep the Statue of Liberty in your yard, I'm guessing, so you have a much smaller version to help you remember that. So when we're saying two things are similar, like these two shapes down here, they can be the exact same shape, just one is the smaller version of the other. Or if you like, you could say it backwards. One is the larger version of the other. One's small, the other one's big. Like if you're ever going to go into architecture or anything, like you want to go build some gigantic thing and have people pay you billions of dollars to build that, well then you're going to have to show them a model of what it looks like. And that's what we're talking about when we're talking about similarity, is that a scaled down version or maybe a scaled up version of that same thing. So angles have to be the same. But here is the part that messes people up. So please, 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 if you're ignoring me, pay attention to this part. The sides have to be proportional. And what that means is that when we compare the sides, we have to make sure that we are comparing the corresponding sides, meaning the sides that are in the exact same position. Notice that AB here matches up with MN. They're in the same position. And AD over here matches up with MP. They're in the same position. DC matches up with PO. They're in the same position. And finally, BC matches up with NO. They're in the same position. So what proportional means is that if I compare the lengths of these two red sides, those two pieces that are in the exact same position, and I compare the two yellow sides that are in the exact same position, and I compare the two green sides that are in the exact same position, and the blue sides that are in the exact same position, if I put them in a fraction together, they will always equal the exact same thing. For example, like notice that the red line, if I were to compare the red line to the other red line, so that's the top of the left one and the top of the right one. Notice that I'm putting all the big ones on top and all the little ones on bottom. It doesn't matter whether you put the big ones, like I'm saying big, I mean the big shape. All the lines from the big shape I'm going to put on top, and all the sides of the little shape I'm going to put on bottom. It doesn't matter. I could do it the other way around too, but whatever you choose to put on top, you must continue to put on top the whole time. So now I'm going to do the blue line. So since I put the big one on top, I'm going to put the big one on top again, AD, over, what am I going to put in the denominator of this one? MP, the exact same side on the other one. And now I'm going to say, well, DC, it matches up with what? PO. And then I'm going to match BC to what? NO. Now, here's the thing. we don't have any numbers for these sides, but we will eventually. And when we compare these, when we plug in those numbers for each side, we're going to find that every single time those fractions are exactly the same. It is the exact same fraction every single time. And that's what makes something similar, is that all of their angles are the same and all of their sides work out to be the exact same fraction. When I compare top to top, side to side, other side to other side, bottom to bottom, they all work out to be the same fraction. Yes, ma'am?
So does that mean what's it called? The size of the smaller shape has to be like a factor of the...
I am so glad you asked, and you are 100% right, but we're getting there. So give me a moment. Where you're going there is exactly where this is. Like, there is, if something is like, let's say that I wanted to make let's say we had some magical machine that could make a scale version of me. Like, I want to make a model of me. Oh my gosh, I have a perfect example that I wish I had brought in. Hold that thought. What we're going to see here in a minute is that the way models are made by computers are using scale factors now, that they shrink things down, or if you have a model of something, like you want to build something based on a model, then you make it even larger. Use a scale factor to make it larger. All right. So here's what scale factor is. Let's say that two polygons are similar here. Like, let's pretend that we've got these two things that are similar. To know that they are similar, two things have to be true. Number one, all the angles in the one have to match all the angles in the other. Would you agree that on the left and on the right, those two shapes have exactly the same angles? Right? The angles on the left match the angles on the right. Okay, so they have the same angle, so they definitely have the same shape. Now, these are not the same size. These are not congruent triangles. It would be improper to call them congruent because they are not the same shape and same size, but they are the same shape. So we could talk about whether these are similar because when we compare the sides, we should get what we call a scale factor, or that fraction that I was talking about. We're going to find out what is that fraction. So what I'm going to do is this. I'm going to take and compare the three sides of one triangle to the three sides of the other. Now, I don't care whether you put the little triangle on top or the big triangle on top. It doesn't matter. Pick whatever you want. But if you put little on top, then you stick with little. And if you put big on top, then you stick with big. Now, I'm going to tell you right now that everything I do, I usually tend to compare left to right. I just tend to do it this way just so you know what I'm doing. I see the first one on the left, so I put left on top. So here are the sides of the left triangle. 3, 3, and 3. Those are all from the left-hand triangle. That's from the left. And on the bottom, guess what numbers I'm going to put? 6, 6, and 6. So we get these three fractions that are 3, 6, 3, 6, and 3, 6. Or if I were to reduce that, these on the right or on the denominator, I would get 1/2, 1/2, and 1/2. What this means is that every side on the first triangle is 1/2 the size of the sides on the right triangle. So if I know the scale factor, and let's say that, like I told you, what if I told you the scale factor was 1/2 and you didn't know any of the numbers? Well, you would actually be able to figure out all the numbers. Because if everything is on the left is half of what it is on the right, so think about this. If the money in your pocket is half the amount that I have in mine, and I've got $50 in my pocket, how much do you have in yours? So I can say this in two ways. If I were to say that the money in your pocket is half of what I have, I could also say that the money in my pocket is what compared to yours? Twice or double. So those are two things. So depending on what we compare, because we put the one on the left first, we put it on top, then we're comparing the left one to the right one. The left one is half the size of the right one. But if we decided to put the one on the right on top, well, then we're comparing the right one to the left one. And then we would say, well, now the one on the right is 2 times the size of the one on the left. So the scale factor could be two different things, but it depends on what you are comparing to what. If I'm comparing the left one to the right one, then the scale factor is 1/2. If I'm comparing the right one to the left one, then the scale factor is 2, because everything on the right is 2 times the size of the one on the left. Does that make sense? Okay, this is the part that gets kind of like, that's the part people struggle with here, is those ratios. A ratio is just a fraction. It's two numbers in a fraction that we are working with here. So you're going to see fractions a lot. The only way that two things are similar is if their angles are exactly the same and their sides work out to be the exact same proportion, the exact same fraction every single time you do it. If it doesn't, they're not similar. All right, here's where we get some work, and this one takes some work. And we're going to be on the slide for a while, so hang on here. All right. You cannot do this slide without this piece of information, so add this up top because you will not be able to do it without this piece of information. Quadrilateral ABCD is similar to quadrilateral MNOP. It means that these two things are definitely similar. Without that piece of information, I can't just say that these things match up. I need to know that they're similar. If you tell me that they're similar, well, now I know which things match up. And just like in a congruency statement where it matches the angles to the angles and the sides to the sides, it's going to do the same thing here. Now, you might be like, well, I can already see which sides match with which sides. Well, what if you couldn't? What if it was like two things that looked really similar and you're like, I don't know which ones match up on this. These triangles are all mixed up. I can't tell. Or these quadrilaterals are all mixed up. We look at it like this. Side AB, right here, matches up with side MN. It doesn't mean that they're equal to each other. It just means that they're in the corresponding position. And those two things will be proportional. And BC will match up with NO. Here's BC matching up with NO. And then we've got CD matching up with OP. Here's CD with OP. And then our last combination was AD and MP. Well, they told us these are similar, so I know that all the angles are the same. But the sides are proportional. Yes, ma'am?
So what you would start off by doing is, what's it called? Dividing like what you have. So what you have is AD is matched up to MP.
Okay, let me talk about what she's doing there because she's going exactly the right direction. If we're going to find the scale factor, we know that when we set up a fraction of...
Can you please resubmit your attendance whenever received it?
Will do. So what she was telling us is that when we compare like the yellow side to the yellow side and the red side to the red side and the blue side to the blue side and the green side to the green side, it will always work out to be the same fraction. But if you look at red and red, if you compared red and red, we're comparing a number to a letter. That's not going to give us a very good fraction there. And if we compare blue to blue, we're going to get a number to a letter. That's not going to work out as a good fraction. If you compare green to green, then it's not going to work out to be a good fraction either because we've got letters and numbers. However, yellow and yellow, if we were to put the 10 on top and 8 on bottom, we would actually get the scale factor. There's no letters in there, but this is a fraction that reduces to what?
It would reduce to 1.25.
Or we'll give it to me as a fraction. Let's deal...
It would reduce to 5 over 4.
Try to avoid decimals. Not that they're wrong, but actually it's so much harder to work with decimals here. You are going to struggle a lot more than everybody else if you're trying to go to decimals, because this shows me that for every 5 units I have on the right, there are 4 units on the left. Every 5 units on the left, there are 4 units on the right. Or what this means is that the one on the left is 5/4 bigger than the one on the right, or 1.25 times bigger, if you will. So we already know now that by comparing the two sides, we know that the scale factor from ABCD to MNOP, meaning put ABCD on top, is 5/4. This is very important because when you compare one thing to the other, it means whatever was first, you have to put on top. Make a special note of that because somebody will miss that on the quiz. I'm telling you right now. That is going to be a thing. I will tell you 2 things to compare. You'll come up to me with your quiz and say, how do I know which one goes on top? And I'll say, hey, remember when we did that slide and I put a little star in it? And you'll look at me and be like, So whatever one is first there when we're comparing 2 things, that goes in the top of the fraction. So since 10 went in the top and 8 went in the bottom, that reduced to 5/4. So my scale factor is 5/4. If it said, find the scale factor of MNOP to ABCD, the reverse direction, then what would the scale factor be? 4/5, just the upside down version of that. All right, now we need to find X, Y, and Z. Now we already know that every single time when we compare the 2 sides, it will equal 5/4. That's a key piece of information. Every single time that we compare 2 sides, it better equal 5/4. So, Amber, you got something?
Yeah, so then you're going to do
times 5.
Well, let's set up, we know that this is equal to another fraction. 5/4 is equal to another fraction.
Yeah, 12 over x. Or
It,
y, so-
good, 12 over y. So check this out. She's looking at the red sides now. She goes, well, since this was yellow over yellow, now she's going to do red over red. Now notice, since the left-hand side, lefts are going in top, she's keep putting the left on top. That's what she has to do. Okay, great. Now we've got this, and this will help me solve it, but how?
Shouldn't we cross multiply?
Yes, exactly. We are going to cross multiply.
And so then you're going to get 5y equals 48.
48.
And then you're going to do 48 divided by 5.
Good.
And we can't simplify that.
It doesn't reduce. I am okay if you leave this as 48/5, but I'm going to tell you at the end that when we're going to have to do something with this number, that I'm going to change it right now because at the end we would have to do it later to make this easy to add. This becomes 9/45 3/5. So 5 goes into 48 9 times with 3 left over, so 9 3/5. Same thing. The only reason I changed it to a mixed number, I don't usually do that, is because I know what we have to do with these numbers at the end, and you're going to see that actually that will be more beneficial to us than the other number.
So you never want us to do a decimal, all this stuff.
I'm going to tell you right now, and I'm going to give you this as my advice, not as a thing. You will probably not use decimals very much again for the rest of your math careers. Decimals are really good in practical numbers, like money. Or I am 1.5 I'm half the way there. I'm 0.5 miles away. But when it comes to things where we actually have to work with them in the equation, actually decimals are not that easy to work with. Fractions are way easier, even if you don't believe me. I get it that there's a hesitation with them, and I can tell you, you may not believe me now, but give yourself 2 years from now, whatever math class you're in, you'll be like, oh my God, if I had to do this with decimals, I'd be dying.
Okay, so why don't you just multiply regularly? Why do you cross multiply it?
Well, let's say we multiplied regularly. Let's go back here. To get 4 out of the denominator, right, we would multiply by 4. And we would get 4 times 12, right? And then to get y out of the denominator, we would multiply by y, and we would get 5 times y. But you know what we just did? We just cross-multiplied. We just did it in 2 steps instead of 1. So you can do it the long way, but when you have 2 fractions that are equal to each other, you can just cross-multiply. It's a really, really fast way of dealing with them. Okay, so we know that y is 9 3/5, but we still need to find x and z. And our key here is the scale factor is going to bail us out every single time. Yes, ma'am.
So you would do 5/4 is equal to 4 over x.
Good. Now she's comparing the blue side. She didn't have to. She could have gone green, but she went blue. That's fantastic. So we are here.
So you get 5x equals 16. And then you divide
So
by
3 1/5, I believe. Check me on that. I make mistakes all the time. So we've got 9 3/5 for y, 3 1/5. Somebody different help me out with z. Yes, sir.
Alright, so then you're gonna put 14 over z. And 5/4 equals.
Good. We need that 5/4. That scale factor is what's bailing us out here.
And cross multiply, so it's 5z equals 56. And we're gonna find
Which is 11 1/5, if I'm not mistaken. Now, you'll realize that you go like, wow, actually, Mr. Hire usually does not convert into mixed numbers, but I'll show you why I went to mixed numbers here. Because now we found x, so we know that 5/4 is a scale factor. We found x, y, and z, but now we need to find the perimeter. And I can tell you, if I'm just adding these up, I would rather add mixed numbers like this, 3 1/5 plus 9 3/5 plus 11 1/5. They're all fifths, so that's super easy to work with. Talk to me about adding these, because there is a very easy mistake to make here. Don't worry, it's not a hard problem, but it's just easy to make mistakes because we don't do this that often. Dylan, talk to me.
I think it's just easier to add the whole numbers first.
Okay.
So 9 plus 11 would be 20, and then plus 3 would be 23.
Okay. I do it, by the way, totally different than he does, but I don't have anything wrong with what he's
You
doing.
would end up adding the ones on the right, which actually equal 1, and then you just add 1 plus
Okay, so it's 23 plus another one. I actually do it the exact opposite way, but it ends up as exactly the same thing. I do the fractions first because then I carry them over into the next slide, but there's nothing wrong with what you're doing. So this ends up as 24. So the perimeter of this one, oh, did I get 24? Oh, I didn't add the 8. I'm so sorry. I was like, that doesn't seem right. We forgot the 8. I forgot the 8. I'll take the blame on that one. Plus 8, the 8 that we already knew there, that was right there. That becomes 32. I was going to say, I didn't get 24 earlier. So the perimeter of this is 32. How am I going to find the perimeter of the other one?
It's just 5/4 32.
You could do that. So she's saying, I know that if I take 5/4 times 32, that I will get that as well. She's right. However, I kind of think there's an easier way to do that. Add up the sides right there. So we've got 14 and 4 is 18, plus 12 is 30, plus another 10 is 40. The perimeter of this one is 40. So the perimeter of each I've now found. Now here's the thing, and this is really important to see because if you get what I'm about to say, you're going to save yourself so much work. If you don't get what I'm about to say, then you're going to create a bunch of work. It says find the ratio of the perimeters. It means compare them in a fraction. So let's do 40 over 32. Can that be reduced?
Yes.
To what? What goes into both? 8 goes into 40 how many times? 8 goes into 32 how many times? Is this number familiar? That was not a coincidence. The way that the sides are compared to each other is all of the sides on the right are, on the left are 5/4 the size of the one on the right, which means that the perimeter on the left is 5/4 the size of the one on the right. So check it out. Let's say that I knew that this was 40, but I didn't know this. For just a moment, pretend that 32 isn't there. I know that 40 is 5/4 of the other perimeter, right? Like that's what we know. So I could turn it into a sentence, solve this, and if I didn't know anything on the right, if I just knew the scale factor, I could tell you about the perimeter. The perimeter and the scale factor are exactly the ratio of the perimeters and the scale factor are exactly the same things. Yes, ma'am.
It's like it has to do with the doesn't like so with all the angles like being equal to each other, just like their corresponding angles. So like in a triangle, if they all add up to 180, is there anything that like quadrilaterals add up to?
Yes, but we don't need that yet. So here's what she's saying. In a triangle, all 3 angles add up to 180. Is there a rule about quadrilaterals? There's a rule about quadrilaterals. There's a rule about 5-sided figures, 6-sided figures, 98,000-sided figures. There's a rule for every single one of them. And you're going to know all of them, literally all of them. I could ask you, if I have a figure that has 1,657,382 sides, what is the sum of their angles? And you will know that very soon, and it will not be a difficult thing. You'll be like, really? That's all it was? Yeah, that's all it was. But we're not going to learn that yet. That's a totally different lesson. It's not a hard lesson, but we're not ready for it yet. I'm telling you right now, it sounds way more complicated. It's super easy, and you'll be like, really? So we didn't have to learn 180? There was a trick that worked for everything? Yes, there's a trick that works for everything. Oh, yes, the ratio of the perimeters is exact same as the scale factor. 5/4.
Was the answer to D just that?
Okay, so this one's nice and easy. It just says, and this is what we just discussed, if 2 polygons are similar, if they are similar, then the ratio of their perimeters, when we set them up as a fraction, those 2 numbers as a fraction, it's going to be equal to the ratio of their corresponding side lengths, or it will be exactly the same as the scale factor. So if you add up all the sides of one of them, like the top, so this is the left one. If you add up all of those, and then on the bottom you add up all of the sides of the blue one, what you're going to have is the perimeter of the left one over the perimeter of the right one. And what will that fraction work out to be? Exactly the same as the scale factor. Every single time. Because if you think about it, the scale factor compares the sides. Like it compares one side to another side. Whereas the perimeter compares all the sides to all the sides. Take all the sides, add them together, compare it to all the sides added together. Exact same scale factor. All right. Last but not least, and this is the one that you're going to have to do very similar type things in the homework, so you might want to pay attention on this one. Okay, if two polygons are similar, then the ratio of any two corresponding lengths in the polygon is equal to the scale factor of the similar polygons. Meaning, if we compare one side of one shape to one side of another, we could get the scale factor. Notice here, it says, right away, it tells us these are similar. They are similar. That's given to us. So, notice here, the only real pieces I have any information about are this side here and this side here. Would you agree that there's two triangles, right? A triangle on the left, a triangle on the right. The only ones that I really have any numbers to compare are that far left and far right side. So I'm going to compare TR to XZ. So they're the matching sides. They are corresponding parts. Well, how long is that left-hand side? It's 12. How long is the right-hand side? 16. So if I wanted to compare the left-hand side to the right-hand side, I could do 12 over 16, and it would give me the scale factor. What does that reduce to? 3/4. The scale factor, when I compare the left side to the right side, is 3/4. Or in plain English, what that means is the triangle on the left is 3/4 the size of the triangle on the right. Now, that is not what they asked me to do. They said, find the length of the altitude. So this is the one we're looking for right there. What could I compare that line to on the other triangle? The 20. Okay, we know the scale factor. We have two sides we want to compare. How could I use that information to figure out that missing side?
You're going to say that, I guess x over 20.
Okay, so she's doing the left side over the right side. That's totally okay. Left side over right side.
Equals 3/4. And I only put the left over the right because I thought that we did that before to get the scale factor.
And you would be 100%. If you had done it the other way, we would have had a problem. So what she said over here is that this 3 came from the 12, and the 12 came from the left side, so that means the 3 came from the left side. The 16 came from the right. When it reduced, that was still on the right. So it was left over right. So when she put her numbers down, she had an X and a 20 she was looking for. She needed to know which one do I put on top and which one do I put on bottom. Well, she had already put the left on top, so she needed to put left on top again. If she didn't, this would not turn out correctly. Talk to me about what I can do now.
So now you're going to do, you're going to cross multiply, so then 4x equals 16. And then divide by 4, divide by 4. And maybe 11. 15. 15.
That's it. So here are some key areas that you got to look out for. Make sure that you are comparing the right piece to the right piece, meaning the matching pieces, the corresponding pieces that are in the same position. If you put like the little shape on top, then continue to put the little shape on top every time. The one thing that we have to be careful about is if it says that let's say it says give the scale factor, this is not something that's on the slide, but it says give the scale factor of ABC to DEF, that means compare the left to the right, and this one has to go on top. When you write it that way, whatever is first has to go on top. That's it. You've got everything you need for this, and you are good to go.